Delta G is the Gibbs free energy, and this is a measure or a degree of spontaneity. From the system, we can calculate that the delta H is equal to delta H minus T delta S. So this will be related with what we have derived for the entropy, which is this one. So now you can multiply the T with the delta S, so you will get this equation, delta H minus T delta S, and we call the process being spontaneous if the delta G is smaller than 0. We call that it's not spontaneous if the delta G is bigger than 0, or this one is minus in value, this one is positive in value, and it is in equilibrium if the delta G is equal to 0. Now note that we normally use a standard condition. Let me write it here. So we have a standard condition that we have also discussed in the previous chapters. And standard conditions is basically the T being 25 degrees of Celsius, or also equal to 298 Kelvin, of course, and also the pressure is 1 atm. And for this, we normally have the symbols of the degree, so we often also see it like this. Now, normally we assume that the delta H and also the delta S, they are not dependent of temperature, or we can also say that they remain constant upon variation of temperature. So although we have the T is not equal to 25 degrees of Celsius, we can still use this equation and we can still use the value of delta H and also value of delta S, because we assume that they remain constant at any T. Now we will discuss the third law of thermodynamics that states that the entropy of a perfect crystal of any pure substance approaches 0 as the temperature approaches absolute 0 or 0 Kelvin. So we can find the absolute value of the entropy, and then this will be used as a reference point of the entropy of other elements at any other states. So in this case, for the entropy, instead of changes in entropy, we normally see the value of the absolute entropy instead. And often the data is measured at the standard condition, so we also often see that this is written with the degree symbol in it to denote that it is measured at a standard condition. And don't forget, the standard conditions is the pressure being 1 atm and the temperature being 298 Kelvin. And just like enthalpy, the delta S, or change of entropy, is also a state function. So it is not dependent on the path taken, but instead it is dependent on the final value minus the initial value, no matter what path or which path were taken to go from the initial state to the final state. Now let's consider that we have a reaction of 2A plus B forming C plus 2D, for instance. Now let's take a look at this reaction. We can find the change of the entropy here also by taking the sum of the coefficient multiplied by the entropy of each of the product minus the coefficient multiplied by the entropy or the absolute entropy of the reactant. So for this particular reaction, we can calculate it this way. 1 multiplied by the S0 of C, and of course plus 2 multiplied by S0 of D, minus the reactant, so 2 multiplied by S0 of A, plus 1 multiplied by S0 of B. Just like how we calculated for the change in enthalpy. So this is sort of identical to delta H calculation that we have discussed in the previous segments.